All right, get ready because today we're going to dive deep into the future of Higgs physics at the Large Hadron Collider.
Yeah, the LHC.
You know that massive underground ring where scientists smash protons together like ridiculously close to the speed of light?
It's incredible.
Totally. And this research paper we've got, it lays out the whole game plan for unlocking even more secrets of the Higgs boson.
Using, of course, upgraded versions of the LHC,
Right.
the High-Luminosity LHC and the High-Energy LHC.
Music to my ears. So it's like we're giving the LHC a super boost, right?
Absolutely.
Not just like a tune-up, but...
Oh, it's a massive upgrade.
Yeah.
Both in terms of the number of collisions, which we call luminosity, and the energy levels we can reach.
Okay, so luminosity and energy, those are the magic ingredients here.
Those are the key ingredients to unlocking new physics potentially.
Because I was going to say, this paper, it frames these LHC upgrades as like gateways to discovering new physics. I mean, that's a pretty bold claim.
It is a bold claim.
Yeah.
But with good reason, this is what's really cool. It argues that by studying the Higgs boson with incredible precision,
Like really zooming in.
yeah, we might uncover cracks in our current understanding,
Whoa.
which would then give us hints to things like dark matter or even hidden dimensions.
See, that's what I love about this stuff. It's just like blows your mind. So let's break it down. You mentioned luminosity and energy, right?
Yes.
So increasing luminosity, what does that actually mean?
So luminosity basically means we're going to have way more collisions, right?
Like way more.
Way more, which means we'll have a much better chance of seeing those very, very rare events that might hold the key to new physics.
It's like trying to find a needle in a haystack, but we're making the haystack smaller.
Yeah, or you're sifting through more hay.
Right. It's like more chances to find that needle. But it's not just about quantity, though, right?
It's not just about quantity. You need quality, too.
Right. We need to crank up the energy.
You need higher energy collisions.
Yeah.
And that opens up a whole new realm of possibilities.
Like what?
It's like if you imagine using a microscope, but now you have a more powerful microscope.
Okay.
So you can zoom in even further
I like that.
and see things that you weren't able to see before. So we have this expanded what we call kinematic range, which gives us access to a wider range of particle masses and energies that are produced in the collisions.
Okay, so this expanded range is like crucial for observing what, rare Higgs decays?
Yeah, it makes it possible.
Things that might happen like once in a blue moon?
Exactly.
Under normal LHC conditions.
Under normal LHC conditions, we'd be waiting, for who knows how long.
Right, but these upgrades could make it possible, and these rare events, they're like the hidden gems, right?
That's what we're hoping for.
That could unlock like a whole new understanding.
Exactly.
Okay, so we got the stage set, right? We're going to have more collisions, higher energy collisions, but now we need to talk about what we're actually going to be looking at. This paper, it really emphasizes studying the Higgs boson's properties in like super high definition.
We want to get to know the Higgs really, really well.
Right, because it's like we found this amazing new particle, right? This is a big deal, but we're still kind of figuring out like what makes it tick.
Yeah, we've only just met the Higgs. Now we need to really understand it.
Exactly. And the paper says that the key to unlocking these secrets lies in something called couplings. What are couplings?
So couplings are essentially the way the Higgs boson interacts with other particles.
Okay, so it's like the Higgs boson's social life, right? How it mingles at the quantum party.
Yeah, you can think of it that way. It dictates how it interacts with its friends.
I like that. And there are two main types of couplings this paper is interested in, right?
And the two main ones are the Higgs self-coupling and then the Euclid couplings.
Okay, let's start with this self-coupling thing. Why do we care about how the Higgs boson interacts with itself?
It sounds a little narcissistic.
Yeah, a little bit.
But it's actually crucial. It's crucial for understanding the very nature of something called the Higgs field, which is this fundamental field that permeates all of space.
Okay.
And is actually responsible for giving particles their mass.
So this isn't about the Higgs boson being like vain or anything. We're trying to understand how this interaction shapes like the very fabric of reality.
Exactly, yeah.
Okay, and the upgraded LHC, that's going to let us measure this with much greater precision.
That's the goal. And the paper suggests that even slight deviations from what the standard model predicts could point towards new physics.
So it's like we're trying to hear a whisper, like a faint whisper in a hurricane.
Right.
And these upgrades are our noise-canceling headphones.
Exactly.
Okay, awesome. So that's self-coupling. What about Yukawa couplings? You said that's how the Higgs boson talks to other particles, right?
That's a good way to put it. It dictates how other particles experience mass.
And the paper, it's especially interested in measuring these couplings to quarks specifically.
Yes, the paper focuses on measuring these couplings to top quarks, bottom quarks, and even the charm quark.
Okay, the charm quark, that one sounds particularly tricky, right?
It is tricky because it's incredibly weak, so it's really hard to measure.
Like finding a snowflake in a blizzard kind of thing.
Yeah, it's like trying to find a very specific snowflake in a blizzard.
But if we can do it, if we can measure that, it would be huge, right?
It would be a major victory. It would offer a really precise test of the standard model
Yeah.
and potentially, again, reveal some inconsistencies.
Okay, so we're talking about pushing the limits of measurement here
Absolutely.
and sifting through massive amounts of data to find these tiny, tiny anomalies.
You need tons of data,
Yeah.
and you need very precise measurements.
But those anomalies, they could be the key to, like, rewriting our understanding of particle physics. This is where it gets really exciting, right? Because these precise measurements could offer clues about some of the biggest mysteries in physics.
Yeah, like dark matter.
Dark matter.
Extra dimensions even.
See, this is what I'm talking about. It's like every time you think you're getting a handle on things, the universe is like, nope, think again.
It's a never-ending puzzle.
Right. And this paper, it's like a treasure map with the Higgs boson as the X that marks the spot.
That's a great analogy.
But we've only just begun to scratch the surface.
Oh, yeah.
This paper is jam-packed with even more mind-blowing possibilities like exotic decays, supersymmetry, and even the idea of the Higgs boson as a composite particle.
And those are exactly the paths we'll be exploring in the next part of our deep dive.
Okay, so last time we were talking about how this upgraded LHC could give us a much, much clearer picture of the Higgs boson.
And its interactions.
Exactly, and maybe even uncover some hints of new physics. But what does that actually mean? Like, what kind of exotic particles, what kind of mind-bending phenomena are we talking about here?
Well, that's where the paper gets even more interesting. It dives into some seriously cool but kind of out there theories.
Like
supersymmetry, extra dimensions, even the idea that the Higgs boson itself might not be a fundamental particle.
okay, whoa, let's unpack some of that. We touched on supersymmetry a little bit last time. Remind me again, what is supersymmetry and why are physicists so convinced it might be real?
Right, so supersymmetry, or SUSY as it's often called, is this idea that for every known particle, there's a partner particle, a supersymmetric partner.
Okay, so like a mirror image, kind of?
Yeah, kind of. They would have these opposite quantum properties. And the reason physicists get excited about CSYs is it solves a bunch of problems with the standard model.
Like what?
For example, the standard model doesn't explain why the Higgs boson's mass is what it is. It should be way heavier, according to our calculations.
So the Higgs boson is kind of like lighter than it should be?
Yeah, it's like it's got some secret diet plan we don't know about.
Mm.
And that's where supersymmetry comes in. These supersymmetric particles, these sparticles, they would interact with the Higgs boson in a way that kind of cancels out those extra contributions to its mass.
So they sort of stabilize it, keep it from getting too big?
Exactly. It's like a cosmic balancing act.
I love it. But finding these sparticles, that's not just a win for the math, right? It could have huge implications for dark matter, too.
Huge. Some of these particles, they're predicted to be stable, electrically neutral, really hard to detect, basically. They fit the bill for dark matter perfectly.
So finding these sparticles at the LHC, it'd be like killing two birds with one stone.
Absolutely. We explain the Higgs mass. We finally find out what dark matter is made of. It would be incredible.
It would be huge. Okay, but the paper doesn't stop there. It also goes into this mind-boggling idea of extraspatial dimensions. I mean, come on, more than 3 dimensions. How is that even possible?
I know, it sounds crazy, but the math checks out, and it could explain a lot. The idea is that these extra dimensions, they're curled up so we can't experience them directly.
They're hidden.
Exactly. But they could still influence the behavior of particles, including the Higgs boson.
So these extra dimensions, they're like pulling the strings from behind the scenes.
So these extra dimensions, they're like pulling the strings from behind the scenes. Yeah, that's a good way to put it.
So how could we actually see them, or at least see evidence of them?
Well, one way is to look for their effects on the Higgs boson. They could affect its interactions with other particles in subtle ways.
So it's like these hidden dimensions are leaving little fingerprints on the Higgs boson's interactions.
Exactly. And the upgraded LHC would be precise enough to potentially see those fingerprints.
That's so cool. Okay, so we've got supersymmetry, extra dimensions, and then the paper throws in this other crazy idea that the Higgs boson itself might not be fundamental.
It's a wild one, right?
It is. It's like saying that, what, protons and neutrons aren't actually fundamental particles?
It's the same kind of idea. What if the Higgs boson is actually made up of even smaller particles bound together by some new force?
Okay, so then how could we test that? How could we see if the Higgs boson has substructure?
Well, we can look at its interactions, how it couples to other particles. If it's composite, those couplings will deviate from what the standard model predicts.
So we're looking for any little discrepancies, any little hints that the Higgs boson is hiding something.
Exactly. And the paper goes into some detail about how we could actually do that at the LHC.
This is incredible. I love how this paper lays out all these mind-blowing possibilities, but then also gives us a roadmap for how we could actually test them.
That's what makes it such an exciting time to be a particle physicist. We have the theory, and now we have the tools to potentially prove it right or wrong.
Last time, we were going down the rabbit hole of supersymmetry, extra dimensions, even the Higgs boson maybe not being fundamental after all. My brain was fried.
Yeah, we were getting into some pretty wild territory.
It's like every time we answer one question about the universe, like 10 more pop up. But that's what makes it so exciting, right?
Absolutely. It's a never-ending puzzle, and we're just starting to put the pieces together.
Speaking of puzzles, this paper dives into this really intriguing model called the 2 Higgs doublet model, or 2HDM.
Right, 2HDM.
Okay, so we're not content with just one Higgs doublet. Now we need 2. I mean, why add another one to the mix?
Well, the standard model, it's great, but it doesn't explain why there's only one Higgs doublet.
Okay, fair enough.
So why not 2?
I like your thinking. But seriously, does adding another Higgs doublet actually solve any problems? Or is it just, like, theoretical window dressing?
No, it could actually explain some things, like, for example, the masses of neutrinos. The standard model doesn't really address that, but 2HDM could offer some clues.
So it's like we're expanding the guest list for the quantum party.
Exactly. And seeing if a new Higgs doublet changes the vibe.
I like it. But does this 2HDM, does it lead to any, like, testable predictions, something we could actually look for at the LHC?
Absolutely. One of the coolest predictions is the existence of charged Higgs bosons.
Charged Higgs boson. Okay, we're really getting into uncharted territory now.
I know, right?
What would finding a charged Higgs boson actually tell us?
It would be huge. It would mean the standard model is missing something fundamental. And the paper actually lays out how we could look for these charged Higgs bosons at the LHC.
So we're looking for, like, a specific signature, a sign that these charged Higgs bosons are out there.
Exactly. Certain decay patterns, specific interactions, things that would really stand out from the background noise.
Okay, so charged Higgs bosons, that's pretty wild. But the paper doesn't stop there, does it? There's talk about models with even more Higgs boson.
Yeah, these are called extended Higgs sectors. Really gets complicated.
So we're talking about a whole family of Higgs bosons, each with their own, like, personality and interactions.
You could think of it that way. And these extended Higgs sectors, they could explain some really big mysteries, like dark matter, or why there's more matter than antimatter in the universe.
It's like the Higgs sector is this whole unexplored landscape, and we're just starting to discover all the mountains and valleys.
And who knows what we'll find?
Okay, but this brings us to, like, the most mind-blowing possibility in the whole paper. The Higgs boson as a portal to hidden sectors of the universe. I mean, that's some next-level stuff right there. Is that even remotely possible, or is that just, like, physicists getting carried away with their theories?
It might sound crazy, but it's not impossible.
Okay, I'm listening.
The Higgs boson, it interacts with so many other particles. It's possible that it could also interact with particles we don't even know about, particles that belong to these hidden sectors.
So the Higgs boson is like a bridge between our universe and these hidden worlds.
Exactly. And by studying the Higgs boson really, really carefully, we might be able to catch a glimpse of those hidden sectors.
Okay, but how? Like, what would we even be looking for?
One thing we could look for is missing energy.
Missing energy. What does that even mean?
So if the Higgs boson decays into these hidden sector particles, they would just disappear from our detectors. We wouldn't be able to see them directly.
Okay.
But we would see that some energy is missing.
So it's like we're doing a magic trick, right? The magician makes something disappear, but we know something's up because, well, it disappeared.
Exactly. And that missing something, that could be our clue that there's a hidden sector out there.
This is incredible. This whole deep dive has been incredible. We've gone from the Higgs boson to supersymmetry to extra dimensions, even to the idea of hidden universes. It's mind-blowing.
And the best part is, this is just the beginning.
Exactly. The upgraded LHC, it's going to give us the tools to explore these mysteries in ways we never could before. I mean, who knows what we're going to find? It's both exciting and, honestly, a little bit terrifying.
I agree. But that's what makes it an amazing time to be a physicist. The universe is full of surprises, and we're on the verge of uncovering some truly incredible things.
So to everyone listening, the next time you look up at the night sky, remember that there might be more out there than we can even imagine. And who knows, maybe one day we'll unlock those secrets and finally understand the universe in all its weird and wonderful glory.